In the previous two podcasts, we saw how atoms are arranged in the periodic table based on their number of protons. The number of electrons that these atoms have is equal to the number of protons, and we can see also that the periodic table helps us to understand how many electrons there are in the various orbitals of these atoms. Bonds occur between atoms in an attempt to give the atoms full outer orbitals. They are more stable when their outermost orbital is full of electrons. Now, ionic bonding is the first kind of bonding I want to look at. There are two main kinds of bonding whereby electrons are either shared or swapped in order to achieve the full outer orbital. In ionic bonding, and here's an example here, we have the two elements that you drew in the previous podcast. We have sodium and chlorine. Sodium on the right and chlorine on the left here. Chlorine with its 17 protons and 17 electrons, and sodium with its 11 electrons. Now we can see that sodium has in its outermost orbital only one electron, whereas chlorine has 7 electrons, but more importantly, it's got space for one electron. I'm going to draw in a space there. Now, chlorine and sodium, if they get together, they can become more stable by ensuring that they have full outer orbitals. And for them, it's pretty straightforward. You can see that if this electron were to shift into this position, they would both have full outer orbitals. If the electron were to move over here, just like this, we can see now the chlorine has a full outer orbital, it's gained one electron, and the sodium has a full outer orbital, it's lost an electron, so now its outermost orbital is full. So now, instead of 17 electrons, we have 18 electrons here, and instead of 11 electrons, we have 10 electrons here. The proton number's not changed. Sodium still has 11 protons, and chlorine still has 17 protons. The number of protons and electrons are now not the same, which means that these particles are now charged. The sodium, as it's lost a negative charge, it now has more positives than negatives, so the sodium gains a positive charge. The chlorine has picked up a negative electron, so it's now got one more negative electron than proton, so the chlorine has now got a negative charge. Now the result of this is just like magnets and opposite poles attracting these positives and negatives, they will attract one another. And these two particles that we now call ions will tend to stick together. Ions are basically charged atoms, and this is why we call this ionic bonding. These two ions, opposite charges, will stick very strongly together. They will bond together. Now if we put lots of sodium and chlorine together, sodium metal and chlorine gas, and we light it and the reaction occurs, we get sodium chloride. Sodium chloride you probably know as salt, and all the particles stick together. The positive sodiums and the negative chlorines all stick together in a big crystal structure, a big giant structure like this. Giant structure or crystal structure. Now if we look back at the periodic table here, we can see where these two elements have come from. We've got sodium here and we've got chlorine here. Remember, each element in this group has one electron space in its outer orbital. Remember, each element here has one electron in its outer orbital. So we can see what's happened. Sodium has given its extra electron to chlorine. This metal has reacted with chlorine, which is a gas, a non-metal, over here, resulting in a total new compound, sodium chloride, NaCl, which has none of the properties of sodium and none of the properties of chlorine. It's something which we eat and is essential for our bodies to function. Based on what we've said, we would probably guess also that potassium might also react with chlorine, making something like this, potassium chloride. Potassium also has one electron available, chlorine has one space, and we would get a compound called potassium chloride. Lithium may also do the same thing. Lithium chloride. Or maybe sodium, or maybe lithium rather, would react with fluorine over here, because fluorine also has one space available, lithium has one electron to give. Lithium fluoride, and so on. Now, elements in group 2, we will remember, have 2 electrons in their outermost orbital, and in the same way as the first group being able to give away 1 electron, elements in the second group, to become more stable, would want to have an outer orbital that is full, would want to give away 2 electrons. Now, would this work? Let's see. Let's take a look at calcium, and let's take a look at chlorine. Calcium is in group 2, which means it has 2 electrons in its outer orbital. Chlorine is in group 7, which means it has 1 space available in its outer orbital. Can these 2 elements combine so that they're both happy with their full outer orbitals? The answer is yes, they can, but calcium wants to give away 2 electrons. For that to work, calcium is going to need to team up with not 1 chlorine atom, but 2 chlorine atoms. Calcium has 2 electrons to give. It's going to need 2 chlorine atoms to give its electrons to. 1 electron to this chlorine atom, and 1 electron to this chlorine atom. We need 1 calcium, but 2 chlorines. The compound would be written Ca, because we only need 1 calcium atom, Cl2, because we're supplying electrons to 2 chlorine atoms. So let's look at some more. How about magnesium and chlorine? Magnesium and chlorine. Magnesium, Mg, and chlorine, Cl. Now, magnesium is in group 2, chlorine is in group 7, so magnesium has 2 electrons to give, and chlorine only needs 1. So again, magnesium will need 2 chlorines to satisfy itself. Mg, Cl2. Now, so that this equation balances, I need to look at the number of atoms here. We've got 1 magnesium, 1 chlorine, 1 magnesium on the right, 2 chlorines, so something's not right there. But it so happens that chlorine, as a gas, always goes around in pairs, so I need to write Cl2 here, 2 chlorines together. Now we can see that this equation balances nicely. And let's look at one more. How about magnesium and sulfur? Magnesium and sulfur. So magnesium is in group 2, 2 electrons in its outer orbital. Sulfur is in group 6, which means it has 2 spaces in its outer orbital. Magnesium and sulfur. Magnesium plus sulfur. 2 electrons to give away. Sulfur would need 2 electrons. So 1 sulfur atom is all that's needed for the magnesium to give away its 2 electrons. So we end up with magnesium sulfide. So that's ionic bonding. In the next podcast, we will cover the next kind of bonding, covalent bonding.